In the previous session, we see the Fubini's theorem. I review this again for you. Suppose x is mu and y to mu are sigma finite measure spaces, and suppose f from x times y to this interval is S tensor to measurable, and this integral with respect to this product measure is finite. Then these two integrals are almost everywhere finite integral with respect to y, and this integral with respect to x is almost everywhere finite. Furthermore, these two functions are measurable. This function is S measurable and this function is tau measurable. And finally we have these equalities. Now we have a suppose x is a set and f from x to this interval is a function. Then the region under the graph of f, denoted by this notation, u by the index f, is defined by this set. The set of all ordered pairs such as x and t, such that t belong to this interval. T belong to this interval from 0 up to the f of x. And you can see this in this graph. This is u f, the set of all x and t, such that t belong to 0 up to the f of x. If we consider x equal to real numbers, of course, because in other cases we cannot see the graph of f. Okay, in the real case we have this, because let me add some slides. Okay, for example, if we consider this function, or this, for example, the value of f considered non-negative, so that if this is our function, for example, and this is or space x, for example, this function, for example. Okay, let this is our x, a to b, for example. Okay, this is our set x. Now for any x in this set, we must consider this line. Okay, because ut equal to the set of all ordered pairs such that t belong to f up to f of x. Okay, if you consider this x, for example, this is f of x. This is f of x. And we must consider t in this interval. Okay. All t in this interval. X fixed and t run up to 0 to this f of x, so that we have the ordered pair x and t run to this interval. Okay, this line, the component, and also other x, other points, okay, such as this. For all of these, we have this in area under our function, so that we have all of this line. T is from 0 to f of x. Okay. The set of all with this property, all of this, okay, all of orders. Shape. All of this, for example, all of this was the second from 0 to f of x. All of these lines. Okay. Not a very nice proposition. Do you have my voice? And do you say yes to my voice? Please pay attention to this proposition. Area under the graph of a function equal the integral. This is suppose X as mu is a sigma finite space, and from X to infinity is an S measurable. Let beta denote a sigma algebra of Borel table, and lambda let the measurable space. This is a set up, and beta is a sigma algebra on this set, so that this is measurable. Then is an element of this sigma beta equal that this definition is set. At first we must put S tensor measurable or UF belong to the algebra, and second must prove equality. Okay. For them, this member, you see that for any natural way, if we put k equal to this and f equal to this, they have equality. If we prove this, since ek and fk are in the sigma algebra, S tensor beta, it's very trivial because this is in the sigma algebra S, and this is of so that this sigma algebra, in fact this is a rectangle, this is the measurable rectangle in this sigma algebra. This is a measurable rectangle, and also this, so that all of these are in the sigma algebra, so that this countable union of element in the sigma algebra must be belong to this sigma algebra. Okay, this countable union must be belong to or sigma algebra S tensor beta. And please note that for each k in N, Okay. Let x is mu be a measure space, and if from x to this interval be a measurable function. Okay, then for each k in natural numbers and for each m in this set, we have the inverse image of this set must be belong to S. It is very trivial because it is a Borel subset of this, because this set, okay, this set is a Borel subset of 0 infinity. Okay, and also this set must be belong to S because this is and Borel subset 2. By the same reason, these two sets are in S, so that these two product sets this product 0 m and this k infinity multiplied by 0k, this okay, must be belong to this tensor product. Sorry, beta. Because these are measurable rectangle, okay. So that this finite union must be belong to this sigma algebra, and since these two are in this sigma algebra, this union must be belong, and this countable union must be belong to this sigma algebra, so that UF must be belong to S tensor beta, okay. But for this equality, please note that at first this union is a subset of EK. Sorry, it's a subset of UF. Okay. One for each K in natural numbers EK and FK are subsets of UF, so that this union must be a subset of UF. And this is very easy, because for example, if we consider an element such as X and T in EF, then X is an element of this set. We must write the axis 1M, because EK is this union. If an element belong to EK, must be belong to one of these product sets. The axis 1 M do. Let me write the axis. Sorry, EK, not EF. Then the axis 1M in this range such that x and t belong to this product set. Okay, multiplied by 0 and so we have x must be belong to this set and t must be belong to this interval. So that f of x must be belong to interval t belong to this interval. And this shows that x and t is an element of UF. Sorry, this is I have a mistake. MK M plus 1K. Okay, these are MK, not this. I explain this for you. MK is true and this must be written MK. And also this. Okay. MK M plus 1K and this interval is MK MK M plus 1K. Okay, and it shows that this x and t must be belong to UF. Because f of x is in this interval So that, let me write by this manner, so that x, so that t is an element of 0 and mk, and mk is less than f of x, so that x and t must belong to u of fk. Okay, similarly, fk must be a subset of uf, and so this union must be a subset of uf. Conversely, let x and t belong to uf. Please note that our function f is from x to 0 infinity. Okay, so that f of x, if this is all 0, for example, 0, f of x is an element in this interval, because f of x is non-negative. Okay, now for each integer k, we can separate this interval by this method. For example, we consider 0 and then one k, one k, 2k, and other intervals. Okay, this may be, for example, nk, n plus 1k, and the last interval by this separating, the last interval obtained by m equal to k2 minus 1, k2 minus 1 instead of m. Okay, k2 minus 1 divided by k and m plus 1, so that this is k2 divided by k, and this is equal to k. Now this f of x may be belong to one of these intervals, or maybe in, this is maybe in one of these intervals, or maybe outside of this. Okay, maybe belong to this interval. If f of x belong to the one of these intervals, if we have these cases, then x is an element of this. Okay, and if we have this case, f of x belong to k infinity, then x must be belong to this inverse image. Okay, since f of x is non-negative, so we have two cases, 1, 2. And so in this case, x and 2 must be belong to ek, and in this case x and t must be belong to fk, so that x and 2 must be belong to ek union by fk, so that must be belong to the union of these sets. Okay, so the inverse of this equality is also holds, and we have this equality, and since all of these are in this sigma algebra, this countable union must be belong to this, and so we prove the first step of this proposition. UF must be belong to this, because UF equal to this union. But for the second goals, for this equality, dear students, do you have my voice? Don't have any? Thank you, Muhammad. For this equality, by the definition of product measure, mu multiplied by lambda, we know that mu times lambda of uf equal to these integrals, and this is equal to this is because this characteristic function phi of uf x and t belong to uf if and only if x belong to x and t belong to this interval. Okay, please note to this definition, x and t such that t belong to this interval and x belong to x. Okay, t belong to this interval, x belong to x. So that we see that phi of uf in x and t equal to phi of x on x multiplied by phi of this interval 0 f of x of t. Okay, and this is equal to 1 because x is the whole of our space. This is equal to 1, so that this is equal to this interval. Okay, so that this integral this inner integral, okay, this integral the integral of C of uf xt d lambda t, because x considered as an fixed. Okay, equal to the integral of this function. D lambda t, and this is equal to f of x, because we know that in Lebesgue integral, let me write one more. C of A and B, for example, D lambda equal to B minus A, and this is our B, this is our A. Okay, so that this integral equal to f of x minus 0, and we have this equality, integral of x, this integral equal to f of x, and you prove the first part of these equalities. Okay, the first part of this equality. And for the second part, you can use Tunnel's theorem 5.28. Tunnel's theorem allows out that change the range of this integral. Okay, so that this equal to this integral by opposite arrange. Okay, integral x, integral 0 infinity, integral 0 infinity, integral x. And now this internal integral equal to this, because so that in this case, by these equalities we have this, and so we have this. Okay, now please note that we have this equalities to, if we fix t we can write x and t belong to UF equal to x belong to this set, the set of all x such that f of x is greater than t and t belong to this interval. Okay, and these two are the same, so that this is equal to x belong to this set, and this is positive, of course. Okay, t f of x, so that phi of UF xt equal to phi of this set, the set of all x with this property. And so that in this case, from this we have this, and so that the integral of this function xt d mu x, in this case t considers as a fixed number, okay, equal to this characteristic function. And d mu x. And this is equal to, let me write smaller than this is equal to mu of this set. Okay, and t and this is very obvious, because the integral of phi of a d mu equal to mu of a, okay, so that we use these two easy facts. Integral of this characteristic function equal to mu of this set. So that in this case, this internal integral equal to mu of this set, and so you prove the second equality. Dear students, thank you Muhammad, and thank you Ali. Dear students, please note that we have this note that Markov inequality, and we can you can see this, and Markov inequality, exactly this inequality, okay? Please, this the only original proposition, Markov inequalities. By Markov inequalities, for any positive real number such as t, we have this inequality, okay? Thus, if we assume that this integral be finite, we can say that this proposition is stronger than Markov inequality, because we have this equality, okay? Or on the other hand, we can conclude by this proposition Markov inequality. We can conclude this. We can conclude this because if mu of this set is greater than this integral, divided by t, okay, then this integral is integral, okay, the second part of this d lambda t, okay, d lambda t must be greater than this integral of this, okay, integral of f of x d mu of x divided by, sorry, divided by t d lambda t. But please note that this is a fixed number, okay? So that we can move this outside of the or integral, so that this is equal to this integral multiplied by this integral. Okay, but we know that this is infinite, so that this is infinite. And this is a contradiction. This is a contradiction because by our proposition we know that this integral equal to this, and we assume that this is a finite number, okay? This is a finite number. We assume that this is finite. This inequality must be whole. It must be okay.
التي أرسلتها لكم على الواتساب وأرسلوا لي بريدا إلكترونيا.
And also this section 5c, okay?
الحل التمارين التي أرسلتها لكم على الواتساب وأرسلوا لي بريدا إلكترونيا. اقرأ لي قسم 5 من الكتاب بعناية وأرسله لي مع شرح كامل. حل التمارين التي أرسلتها لكم على الواتساب وأرسلوا لي بريدا إلكترونيا. اقرأ لي قسم 5 من الكتاب بعناية وأرسله لي مع شرح كامل.
It is clear? Okay, thank you very much, and thank you for your attention. we follow in the next session inshallah. Goodbye for now.